you are, yeah. I apologize for the quality of the lecture, of the makeup lecture. There were a variety of issues. One was that the lecture was abbreviated because I didn't realize that there was a big class coming in, and kind of got started late because I was trying to figure out the technology. But in addition, I forgot to put the microphone on until about 2/3 of the way through the lecture, so I won't forget that again. If you do have problems with quality at any time, please let me know, because as a practical matter, I'm the person who has to kind of try to coordinate it. I mean, I can go, if you can identify what issues are, I can go to the EP folks, and I can also go to the ITAP people, and I can try to get the problems resolved. But let me know about it. Don't be bashful about that, okay? Let me see. Where we last left off, I'll go to the document camera now, because I know you like that better. Where did we leave off? Oh, we were doing gradient descent, right? So we were doing the convergence analysis of gradient descent. So there's kind of a clever little thing here you can do. So we're supposed to get through what section in this lecture? Slide 23. Oh, okay. We're on track. So basically, in gradient descent, this is the basic iteration that you compute the gradient, you move in the opposite direction. Okay. And then what happens is that, well, if you have to calculate the gradient of the quadratic function is this. Okay, it's A transpose 1 minus AX plus BX. So that's equation 5.11. And then you plug that into the expression for the gradient descent, and you get equation 5.12. Okay, and if you rearrange terms, that's 5.13, you get the new value of x. X is the solution that you're trying to calculate. So you're iteratively. xk isn't the solution to the optimization, but it's a step along getting the solution. Okay? So you're now doing the sequence of updates, and hopefully they'll eventually converge to the minimum. And the minimum will be the solution to your problem. So the new value of x is the old value of x times this matrix here. Now the matrix is the identity matrix minus the constant times A transpose sigma squared B. So, and then there's this additive constant, okay? Now, it turns out, obviously, the additive constant, alpha times A transpose Y, is very important because it's what gives you the correct answer. Otherwise, if this were 0, then basically the solution to this iteration would be 0, okay? It would be very uninteresting. But this driving term is important because the particular solution of this difference equation is what you're interested in. But if you want to understand the convergence of the difference equation, you're only really interested in the homogeneous solution, okay? Which digging way back, deep into your subconscious mind, and you'll remember when you were undergraduate, you learned about differential equations, and they had homogeneous and particular solutions, right? So you're interested in the transient part of the solution, which is the homogeneous solution, basically, okay? So what you can do, there's kind of a clever trick you do here, which is that, so this whole thing here is what? Okay, I need a little bit of notation here, just a moment. But I don't want my notation to be completely different. So basically, you take this thing here, this part here, okay? And that matrix there, I don't want to have to write out because it's kind of a mess. So I'll write it as H, okay? It's a constant matrix. So we have that H is equal to A transpose A plus sigma squared B. H is a symmetric positive definite matrix, right? Why is it symmetric? It's symmetric because if I take its transpose, this is symmetric, right? And the transpose, the A transpose, oh, by the way, just as a, if you have A times B transpose, that's equal to B transpose A transpose, right? And if you have A times B inverse, that's equal to B inverse A inverse, assuming those quantities exist. Okay, so that's so that's how you apply those. It's generally true. So here, if I took the transpose of H, I get the same thing back. So it's symmetric. It's got to be positive definite. How do I prove that it's positive definite? Well, to prove that it's positive definite, I have to prove that X transpose HX is greater than 0 for all X, right? That's the definition of positive definite. So if I multiply this, I get X transpose A transpose AX plus sigma squared X transpose BX, right? Now, this is positive definite, so it's got to be greater than 0. I mean, that's by definition assumption. Well, B is the inverse covariance matrix, right? So it's got to be positive definite. So that's got to be true, okay? Then this thing, whatever this thing is, I'll call it X tilde, and I'll call this X tilde, right? It's the same thing. This is X tilde transpose, right? So this is just X tilde norm squared. Well, that's got to be greater than 0 too. Greater than or equal to 0. I'm assuming A here is not singular, so if the only way this could be equal to 0 is if X is 0. So for all, I should put here all X greater than 0, right? Obviously, if X is 0, then, or I guess another way I could do it would be for all X not equal to 0, not equal to the vector 0. All right? Okay, so everybody's familiar with this. I think probably this should be reviewing soon, but, okay, so you have H is equal to A transpose A plus sigma squared B, right? So the equation then is that xk plus 1 is equal to I minus H, right? Yeah, minus, I wrote that incorrectly. Let me just redo this. X to k plus 1 is equal to I minus alpha H times xk plus some constant, okay? And the constant here was alpha A transpose Y. But that's not going to change. That's a constant, right? Now, let's hypothesize that this thing converges. If it converges, then it would mean that you keep running it and forever, and eventually the x doesn't change anymore, right? So, x then, I'll call x infinity, that's equal to the limit as k goes to infinity of xk, right? Now, well, if that's true, then it must be, when you get to that infinite point, I'm like playing a little bit of games. There's some like various limits that you have to take, okay? But intuitively, I think it's pretty clear from an engineering perspective that if this thing converges to a limit, right, I can take the limit on both sides of this equation, and I get that x infinity is got to be equal to I minus alpha H times x infinity plus alpha A transpose 1, right? So I have to reach a stable solution. Now, if I subtract these two equations, what I can do is I can say, well, epsilon, I want to make sure I use the same definitions here so I don't confuse you as I have in my notes. So if epsilon here is, so if I define epsilon k is the error, and if I say that's going to be xk minus x infinity, right? Well, what does that mean? It means that epsilon k plus 1 is going to be equal to I plus alpha h times epsilon k. And what will happen is that this constant term subtracts out, so it'll be plus 0. So this is a really interesting equation because it tells you how the error decays. Now, see, you don't really know what epsilon is because you would have to actually know x infinity. And if you knew x infinity, you'd be done to start off with. But we're assuming there is some x infinity, we just don't know what it is. And our error, is going to decay according to this equation. Now you have to understand, what is the error here? The error is not, in this case, epsilon is not the difference between the correct answer and your answer. It's the difference between the map estimate and your answer. So x infinity is going to be the map estimate, but the map estimate is not correct either. So you're breaking down the errors into different pieces. This is a point that's often confusing to students, okay? That you have the true answer, we'll call that x star. That's truth, okay? And then we have our best estimate of truth. That might be x map hat. That's our map estimate, okay? And then we have but the problem is calculating x map hat is hard. So what we have is we have xk, right? So xk is an approximation x map, and x map is an approximation x star. So we're breaking these errors down into their pieces, but you have to understand that this x map here is just x infinity, because we're hoping that when we converge with gradient descent, we eventually get to the map estimate. But just because we've driven the error in our calculation of the map estimate to 0 doesn't mean we have the right answer to the problem. We'll never have the right answer to the problem because we have to be omnipotent, okay? All we can do is we're going to try to do our best estimate, but we at least want to calculate our best estimate correctly. Is that clear? Okay, good. At least you're politely nodding. So this is the equation which governs the decay in the error to the correct calculation. Now what happens is that you say, okay, well, look at this matrix here. I'll call this matrix P. It's also a symmetric matrix, but it's not necessarily positive definite. That's not a plus, that's a minus, okay? Now, so P here, P is this matrix, and it's equal to I minus alpha H, okay? So, let's say H, so is P positive definite? Well, first of all, is P symmetric? Yes. Is P positive definite? Yeah, not necessarily, right? Why? How would you make P, how would you drive, what are the eigenvalues of P? So let's first look at H. Okay, let's assume that we have some eigendecomposition for H. So then it would be called E, and what do I use for the, hold on to it, lambda E transpose, okay? Now, let me make sure everybody's on board. H is a symmetric matrix. Do you remember what it is? H is defined as A transpose A plus sigma B. A is the forward projection operator. So remember, in our problem, we're observing. Let's wind this back and make sure everybody's on the same page, so we haven't forgotten what problem we're solving. Okay. We observe y equals ax plus some noise. A is A. It's the matrix which we don't directly observe x. We observe it through this operator A. And A might be like a blurring operator, or it could be tomographic projection, it could be an electron microscope, okay? W here is noise that's additive, and we're assuming that the noise is additive with its covariance, its inverse covariance is lambda. Okay, I think here we assume that inverse covariance was just I times sigma squared. So they're independent noise with variance sigma squared, okay? So with those assumptions, H was this, okay? And then the gradient descent, the decay of the gradient algorithm looks like this. Okay? So now H is defined as we'll put here A transpose A plus sigma squared V. So H is a symmetric matrix that's positive definite, so it has some eigendecomposition. By the way, what do you know about the eigenvectors of a symmetric matrix?
No.
Okay. So everybody's looking down, which is a bad sign. Okay. First, everybody look at me.
No.
You're looking at me like really briefly, and then you're looking away, because you're afraid I might ask you a question. Okay. I promise I'll ask you an easy question now, okay? Let's pick a matrix that's easy. We'll pick a matrix, we'll pick a letter R, okay? Let's say R equals R transpose, okay? So it's a symmetric matrix. So what do you know about the symmetric matrix? What do you know about the eigenvalues? R is equal to what? You haven't. Okay, I'll give you a clue. Think that R is a covariance matrix. Then what do you know about its eigenvalues and its eigenvectors? Tell me anything.
Orthonormal.
Tell me something that's wrong. Okay. Being wrong is the first step to being right. That sounds like eigenvectors are okay. Huh?
The eigenvectors are orthonormal.
The eigenvectors are orthonormal. That's correct. You see? I knew you could do it. Okay. So R, okay? Let's just do a quick review here. We have a covariance. So what's the covariance? So let's say we have a random variable. So R here is the expected value of x transpose, say, where x is as a random vector, okay? So that's, and let's say it's zero mean. So the expected value of x equals 0, okay? So the expected value of x is equal to 0. And R is the covariance, okay? Now, yeah, okay. So R is going to be a symmetric matrix, right? And let's say we do a scatter plot. In 2D, what was the scatter plot for a Gaussian? And let's say x is Gaussian, right? So what's the scatter plot look like in general? Is anybody else there? Someone just volunteer some incorrect information, okay? I'm going to bring candy bars in here. Okay? Come on. Just say anything.
That's football.
It's going to look like a football, okay, of some kind of thing, right? Have you ever done scatter plot of data? Like this is the average number of Tootsie Rolls people eat, and that's their waist diameter, circumference. More Tootsie Rolls, bigger waist, okay? Is everybody, hello? Is anybody home? Okay, now, so you're going to have some correlate, that's called correlation, right? Right? And each of these samples will be a point in 2D, right? And then you calculate the autocorrelation, and you'll get an autocorrelation matrix. So what would the autocorrelation matrix look like in this case, okay? It might look like, it's a 2 by 2 matrix, right? And it would have like, you know, this is sigma x, this is sigma 1 squared, and this is sigma 2 squared, right? And then this is going to be, rho, the correlation coefficient, times sigma 1 times sigma 2. And this is going to be rho times sigma 1 and sigma 2, okay? Everybody knows that, right? That's just, okay. Everybody feeling good? So now, if you have this case, oops, it should go through the center, then the correlation would be positive, right? Because these are correlated positively, right? That's the football. Now, what are the principal components of this correlation? What are the principal eigenvalues of the correlation? You remember? Is anybody home? Hello? Somebody answer me? Oh, just to make me feel good? Give me a wrong answer, please. I'm begging you, okay? Okay. You know anything about correlation? Because if you don't, I'll just teach it to you right now. You guys know this? You're looking like you're trying to avoid eye contact. So I'm assuming that you don't know this, or you do. You've seen correlation before? Okay. Is everybody there?
Plus 1 minus.
Huh?
Plus 1 minus.
Okay. It's like you take x1, the first component, times x2, right? And you if you compute the expected value, right? And that's this thing here, right? Okay. Now, if you take the eigenvectors of this matrix, okay, they're going to be along the axes of the football. You did this in homework 1, right? This is a great exam question. And what's this length going to be?
Sigma squared, each one.
Actually, very close, but not quite.
So the sigma instead.
Sigma, okay? Because this is going to be like sigma 1, and that's going to be sigma 2, assuming that they're ordered from in size. Usually, you take the eigenvalues and you order them in size, right? And this is going to be E1, and this is going to be E2. Those are going to be normal vectors. And you can express the autocorrelation R like this. You can say, this is E1 and that's E2. Those are that's a 2 by 2 matrix because E1 and E2 are each two-dimensional vectors, right? And then we're going to have this thing here, which is going to be sigma 1, okay, squared, and sigma 2 squared, and 0, 0, right? Those are the eigenvalues. And then this is going to be E1 transpose and E2 transpose, right? This is just how this is a way of expressing autocorrelation. You diagonalize them, okay? Are you guys with me now? I'm still sensing this sense that this reluctance to make eye contact. Ask me a question. Don't be timid, okay? Because I would rather you stop me and ask me this, okay? Because I need to hook you into this, even if it's at a basic level, and then we can move on from there. But if you're just, like, not understanding anything I'm saying, it's not going to be helpful, okay? So ask me a question. I'm requiring that you ask me a question, okay? Okay? You can ask me any question you want. You can ask me my mother's maiden name. Something, okay? I'm going to go through, and I'm going to force everybody to ask me a question. I'm going to start over here because you guys are the most quiet, and I'm a kind of an intrinsically cruel individual, okay? So you have to ask me a question, okay? Do you have any questions about that? Anything. It could involve the meaning of life.
I have a question.
Okay.
So, I mean, I'm not really familiar with this format. I mean, for autocorrelation, I use the kind of integration format, and I cannot really kind of match this too.
Yes, thank you so much for your question. Okay? By the way, I'm going to take some time and do this, and you guys still have to keep reading the notes, okay? But this is like, you need to have this kind of stuff solid in your head. So it's very important, okay? And then go back in this first chapter, we were doing some of this stuff, okay? But if you don't understand, you have to ask me. okay? Because I can't read your mind. So what happens, you're thinking of, okay, how many people in this room do experimental research? Okay, that's an threatening question, I think, okay? How many people here do experimentally oriented research? How many people here do theoretically oriented research? How many people here do not do any research? Okay? You gotta put your hand up for one of those questions, come on! Work with me, guys! Work with me, okay?
Simulations aren't experiments,
Okay,
right? It's like...
yeah, they count. Okay. How many people here like pizza? We'll start off with something simple. How many people do not like pizza? Okay, good. We're making progress. Okay. So just think of probability distributions as being like pizzas that are oddly shaped. Okay. Now, so you have. Remember, if you just took a dart, okay, and you threw it against the wall, okay. Now, if you were like really good at playing darts, you get a circular pattern. But if you've been drinking too much or something, or had a broken arm, okay, you might find that the pattern would be skewed like this, okay. And then you find the center of the pattern, so you get a bunch of points, right? So each point can be represented as a vector in 2 dimensions, right? This is x1 and this is x2, right? So now you could form a vector x is equal to x1, x2. Well, you'll get a new vector for each value of the sample, for every new sample, right? So you can represent the center point as a set of points. You get x1, 1, x2, 1, then x1, 2, x2, 2. And so you come to xn1, x2n, I'm getting this all mixed up. x1n and x2n, right? So this will be a 2 by n matrix, right? Now what you do is, so this thing I'll call x. You take x, okay, transpose times x times 1 over n, and that will be an estimate of the autocorrelation. The other way of looking at it is for each point, you take the sum, you sum over I equals 1 to n of, this is x1i, x2i, times x1i, x2i, right? That's, and you also have to divide by n. That's the sample autocorrelation, right? Is everybody familiar with the sample autocorrelation? So now, the variance then, okay, so now you'll have 2 axes of this. So if you drew the scatter plot, you could draw an ellipse, okay? And the ellipse will have the following form. So you have a scatter plot, right? People have done this before, right? In like MATLAB or by throwing darts against the wall, they've seen that you can get a scatter, right? And then you could actually draw an ellipse of the distribution, right? The contours of constant probability of this distribution have the form x transpose at Rx equals a constant. That is the generic form of the equation of an ellipse. The other way you could put it is you could say left center equal to, if you want to fill in the centers, okay? So that is the equation of an ellipse. And this ellipse will have 2 axes corresponding to the 2 principal components. This is going to be the first eigenvector, this is the principal eigenvector, and this is the second eigenvector, okay? And this width here corresponds to the eigenvalues, is actually the square root of the eigenvalue. So you can write this matrix R as E1, E2 times the diagonal matrix, which will be sigma 1 squared, sigma 2 squared, 0, 0, and then this is E1 transpose, E2 transpose. Right? So these are called the eigenvectors, and these are called the eigenvalues. The E is the eigenvectors, and lambda is the eigenvalues. This is a diagonal matrix, and this thing is orthonormal. By orthonormal, I mean that E transpose E is equal to the identity matrix. Okay? Does any of this look vaguely familiar? Okay, I forget where I was. Okay, getting back to our original problem, we're trying to understand the convergence of the equation epsilon k plus 1 is equal to I minus alpha h times epsilon k. All right? Now, so how does this converge? So what we do is we take this. We take H is a symmetric positive definite matrix. So it has to be representable in the form E lambda E transpose. Okay? Where E times E transpose equals the identity. And lambda here is diagonal, and its entries are, I'm calling them H1 through I forget what the dimensionality of this problem is. This thing would be N, I guess. N is the number of pixels in an image, I think. So I think it's N. Okay? Okay, are you okay with that? Okay, good. I got some eye contact there. It's small. I got a little bit. I'm desperate. I'm like a person dying of thirst, okay? Like, this is a desert, okay? And I'm over here, and I'm like, okay, I'm over here, I'm on my hands and knees, hold on. All right. So there are my arms, okay? And like over here, a little cup of water, okay? That's a little umbrella here. Okay? I'm desperate. Okay? You've got to give me hope. Hope for the future, okay? Okay. Give me something, okay? Okay. Now, so you got this. Okay? Now what happens is this, and this is the clever part, okay? I can do this. I can say, so what I can do is I can say, I'll take EK tilde, oh my God, EK tilde is equal to, I guess it's E transpose epsilon k. So I'm basically doing, an orthonormal transform is like a rigid body motion. See, I can make this and these eigenvalues decorrelated, okay, by taking, I can diagonalize this matrix by rotating this thing so that the ellipse is aligned with the axis. So when I do this rotation of the coordinate system, sometimes it's called principal components analysis, I'm going to decorrelate these. And if you just plug it into the equation, what you'll get is this. You'll get that E tilde of k plus 1 is equal to I plus alpha, or minus alpha lambda times epsilon k tilde k k. So, okay, so you say, well, what's the big deal? Well, the big deal is now this is diagonal. The I is diagonal and the lambda is diagonal. So these set of equations are now decoupled. Each dimension evolves independently. So here you get that epsilon tilde k plus 1 is going to be equal to epsilon tilde of k. The i's dimension of that will be equal to just 1 minus alpha hi like this. So if I want to calculate it for any value of k, I just take 1 minus alpha hi to the k and multiply this by alpha I as 0. So basically what happens is you get decay in time, and the rate of decay is equal to this factor. I mean, this is actually a pretty beautiful thing, okay? It says that when you have an equation like this, if you take 602, how many people have taken 602? Okay, oh, beautiful. I'm getting some engagement here, okay? I saw you like drawing things with your fingers, okay? Do you have any questions? Does this make sense to you?
I have one question in second line from the bottom.
From the bottom here?
Yes.
Yes.
I don't understand I don't understand 1 minus yes, right.
1 minus hi? Okay, so you understand this line here?
Yes.
Okay, so this is a diagonal matrix, right? So what happens, let me just write it out. So this matrix, I minus alpha lambda, right? That really looks like this. I looks like this, 1, right?
Yes.
And then this is minus alpha, and then lambda, I said, is h1 through hn, and these are all zeros, right? So that means this matrix really looks like this. 1 minus h1, and it's 1 minus h2, and 1 minus hn, right? And everything else is 0. And then when I multiply by that, well, each coordinate just evolves independently. See, okay, let me rewrite this thing. I'm so excited, okay? Let me write this, okay? This is the, can I give a new letter to this so it'll make it easier for me to do? So 1 minus h1 I'll call, give me any letter. Give me your favorite letter.
It's okay. I understand this.
Oh, you got this? Okay, so that each coordinate now evolves independently. So when each coordinate evolves independently, well, if you just multiply by some number, then if you multiply by that number 10 times, you've just multiplied by that number to the power 10. So this is the decay rate. This is how it evolves with time. So each mode of the error in your solution decays exponentially with the rate 1 minus alpha hi to the k. So, now, remember, think back, h was, we had no choice about. H was, in this hailstorm of paper, h was this A transpose sigma b. We don't have any choice about that because alpha A here is the system matrix. It's actually the model of our physical system. It's like our electron microscope or our flatbed scanner or our telescope looking into space, okay? It's the thing that relates the thing we didn't know to our measurement. B here was the inverse covariance matrix is for the thing we're trying to reconstruct. So B is something we assume, but this is our prior model, this is our forward model. So we can't change these, they're part of the problem, okay? And H is the result of that. So these HIs are given to us. What we can change is the alpha. Alpha was related to the step size of the gradient descent. We can make alpha big or small, or we can even make it negative if we want, okay? We won't want to make it negative, but we could make it big or small. Well, what would be the best choice for alpha? Excuse me? 1 over h of I, right? Why? Because then this expression would be 0. And 0 times 0 is 0. Okay? So then the error would go to 0. Okay? And if we can't make it 0, we can at least make it small, right? If you make this 0.1, 0.1 to the power 10 is 1%. So in 10 iterations, you're down to 1% error, okay? But what's the problem? The problem is that alpha is not a function of I, but h is. So, let's say you have the following thing. Let's say you plot out the eigenvalues. You plot out the eigenvalues, and let's say the eigenvalues look like this. The eigenvalues look like what? Okay, so it's a, let's say the eigenvalues look like this. Okay, so this is I, and this is HI. You're saying, well, why would it be smooth? Okay, hold on to that thought, okay? Because H can be viewed as the frequency response of a filter, okay? Because remember how we did that crazy problem and you looked at me and you thought, what's this guy having me do? Where I had you relate the eigenvalues of a matrix to the DFT of the underlying kernel? Well, that's this. The eigenvalues of this matrix are related to the Fourier transform of the filter response, if it's a phase invariant filter. So let's say these are your eigenvalues, right? Now what you want to do is you want to subtract, and then what happens is that you have the value 1 as 1, right? And then you say, okay, now I'm going to have, this is h, this is 1, this is going to be 1 minus alpha h, right? Well, what's it going to look like? It starts off at 1 here, or close to it, and it's going to go like this. You see? Because I take this function, that's the first function, and then this is 1, and I subtract from 1, I subtract this, I'm going to get something that looks like this. Now, if I make alpha really big, what will happen is that this dip will go down, eventually it'll go down negative. If it goes down below minus 1, what's going to happen? So here, so we're going to have rho I, say, is equal to 1 minus alpha h I, okay? So if rho is, say rho I is equal to minus 2, then what's going to happen? Say it loud, say it with gusto. I mean, even if you're wrong, hey, you know what? You know, there's something really interesting about the world. Like, you know when you watch politicians, national politicians on TV, do they ever act like they don't know the answer to something? They go, we're going to do this. Right? Why? Because they have no idea what they're talking about. But they just say it like they do. Okay? So, belt it out with gusto, and who cares if it's wrong?
I think the side of 1 minus alpha hi, the side of the power will flip.
If you do this and you have minus 2 to the k, it'll go crazy. It'll go ding, 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 and it'll blow up, right? If you have rho I equals plus 2, what would happen?
So
Well, that would be really silly. That would be like using the negative value of alpha, okay? But then what'll happen? It'll go up, okay? So in order for it to be stable, you need that rho I has to be less than 1, correct? Okay? So fine. So you could adjust this so this first eigenvalue is 0, or make it less than 1. We'll just make it 0 because it's simple, okay? But then what's going to happen? These other values get bigger. So that's what these equations here are, which I'm sure you've studied very carefully, right? You read this section here very carefully, I know, because I trust you, okay? these are the equations, right? That these things converge, you need, so if you define, so what you can do is you can select alpha to be 1 over the largest eigenvalue, right? If you make it 1 over the largest eigenvalue, then, okay, well that's a reasonable thing. For the large eigenvalue, you'll get convergence in a single step. Okay? But now for the other eigenvalues, what's going to happen is you're going to get, like, well, let's say the minimum eigenvalue, you're going to get 1 minus alpha min, so that what will happen is that this expression will be 1 minus the min over the mass to the k. So if the minimum eigenvalue is really small, and the maximum eigenvalue is really big, this ratio is going to be a very small number. Right? Yeah?
What controls the span of the eigenvalue?
Hold that thought for just a moment. Okay? So the span of the eigenvalue is called the condition number, and it's very important. Okay? So the condition number is some number. If it's 10, it means that the largest eigenvalue is 10 times larger than the smallest eigenvalue, right? If that's the case, then this number here will be 1/10. And then 1 minus that will be 9/10. And then this thing will converge slowly. So what does this say? If the condition number of the problem is high, the convergence of the worst eigenvalue is going to be slow. Does that make sense? You understand that? So now the problem is the condition number is related to what? It's the eigenvalues of the matrix. The condition number, first of all, what is the matrix? And we're taking the condition number. The condition number is the matrix H, which is equal to A transpose A plus sigma squared B. Now, if the condition number of this is going to be, we take the eigenvalues of it, okay? The eigenvalues are going to be like, we could plot the eigenvalues. We'll get, this big eigenvalues, and then we'll get a small drop-off. What will happen is that if you have a blurring kernel here, so let's say A was a blurring filter, and the filter had a very steep cutoff, then the smallest gain of the stop band gain, the ratio of the stop band gain to the pass band gain squared is the condition number, because you're taking A transpose times A. So this condition number could easily be 10 to the 6, or even bigger. It could be 1,000,000 to 1, because if your filter has an attenuation of 1,000 to 1, or 100 to 1, or even 10 to 1, this could be a big number. So the convergence of gradient descent is going to be very poor in this case. Okay? Now, what happens is, if you're doing a deblurring problem, then what will happen is that the eigenvalues, the large eigenvalues are at the low frequencies. This is actually just like a deblurring problem, because if this was frequency along this axis, at the low frequency you have the large eigenvalue, so when you take 1 minus that, you get the small value here. So that means what? That the low frequencies converge fast, and the high frequencies converge slow. That's what will happen with gradient descent when you have a deblurring problem. If you're solving a differential equation, when you're solving a differential equation, you're not doing deblurring. The forward operator A is actually a derivative. So when you're solving a differential equation with gradient descent, you actually get the high frequencies converge fast, and the low frequencies converge slow. Okay? But if you actually, if anybody's ever solved a differential equation with like Jacobi iterations, that's how it works. Okay? So this is actually, read the chapter, okay? And then come with questions. Any questions? Like, I'm desperate for questions, okay? I'm like this person in the desert who I drew, okay? Look, I have to be desperate or I wouldn't draw this picture, okay? Okay? Have some mercy on me and come with questions, okay? Please. And I'm going to like put the dot thing back on here, touch the screen, so I can say goodbye, okay? But, okay, so you're going to come next time with questions, okay? This is really simple stuff, but you have to understand it. Because mostly what you need to get out of this course is not a bunch of complicated equations, okay? It's a few simple ideas that I want you to take away that you can actually use, okay? And so look at the notes, and try to understand, and then come back. Okay, I'm done, whether I want to be or not. Okay, good.